A rational function is any function which can be written in the form f of x equals g of x divided by h of x, where g and h are both polynomial functions. I'd like to take a look at some examples and their graphs. Let's start with this one. We've just been talking about transformations of functions recently, so you right away should understand the graph y equals 1 over x, which you know is a hyperbola in standard position. Its axes, the axes are the vertical and the horizontal asymptote for this function. This graph is just this graph shifted over 2 units to the right. So if we have y equals f of x equals 1 over x minus 2, we take this initial graph and shift it over 2 units to the right. The vertical asymptote shifts over 2 units to the right, everything shifts over 2 units to the right. And we end up with a graph which looks very much like this. By setting x equal to 0, we end up with 1 over 0 minus 2, negative 1/2. We can see that this graph crosses the y-axis at negative 1/2, in case we were interested in the y-intercept. Let's take a look at another example. F of x equals x squared. Now, if we look at that, we might say to ourselves, wait a minute, that is not a rational function, that is a polynomial, and you would of course be right that it's a polynomial, but it is also a rational function, because I can write this as x squared divided by 1. I have a second degree polynomial on the top and a 0th degree polynomial on the bottom. The largest power of x is x to the 0. And we of course know what the graph y equals x squared looks like. It's just a parabola in standard position. So from this we can observe that any polynomial is also a rational function, because I can write it as that polynomial divided by 1. So the class of rational functions is larger than the class of polynomials, since it includes all the polynomials. I want to take a look at yet one more example. K of x equals x divided by x squared minus 2x. Looking at this thing, we may be tempted to factor an x out of the denominator, and this would certainly be an intelligent thing to do. And quite correct so far as we've gone. It may be tempting now to try to cancel this x on the top with this x on the bottom. And if we do that, we'll find out that we actually have made a mistake. This graph, this function right here, and this function right here are not equivalent. You can see that that's the case because up here, if I plug in x equals 0, I end up with 0 divided by 0, that's garbage. But if I plug in x equals 0 down here, I end up with 1 divided by negative 2, negative 1/2, that makes sense. So this is not defined at 0, whereas this is. So this equal sign right here is not in fact correct. I can make it correct by putting a caveat in here. I can write except where these two are different, and the only place where they're different is at x equals 0. Now this equal sign is correct. We already know what y equals 1 over x minus 2 looks like. We know that has a vertical asymptote at x equals 2 and is shaped like a hyperbola. the graph y equals k of x equals x over x squared minus 2x. We'll discuss that graph in more detail, how to draw such a graph in more detail later in the semester, but let me just show you right now the difference between this and this. This one also has a vertical asymptote at x equals 2. And as we said before, the only difference is what happens at x equals 0. At x equals 0, this crosses the y-axis at minus 1/2. Whereas this graph actually has a hole in the curve at x equals 0. The graphs of rational functions are continuous except at the x values where the denominator equals 0. The denominator equals 0 twice, once at 0 and once at 2. 2 happens to be a vertical asymptote in this particular picture. At 0, we have a different problem. We have a hole in the curve. And again, later in the semester, we'll learn how to distinguish which places where we have a 0 in the denominator are actually